Hello, my name is Kevin Kim, and this is going to be my Lab 3 submission for physics. And to get into the introduction, we have two parts for this lab. Part 1 is analyzing the star's motion to estimate the mass of the black hole. Part 2 is utilizing the estimated mass of the black hole, mass of the moon, spaceship, to find the initial velocity of the spaceship, to find a way to orbit around the planet and the moon without it crashing. We demonstrated Newton's second law and its relation to momentum when conducting this lab, and only glow script was used because it was simply coding. And to get into some fundamental physics used in the lab, Newton's second law, of course, as used in the last two labs, is F net equals change in momentum over change in time. And if we manipulate this formula, we can get that the total net force is equal to the net force parallel plus net force perpendicular, which just means that all the forces combined are equal to the net force. And for this lab, we will need the gravitational force formula, which is that the gravitational force is equal to the gravitational constant times mass 1, mass 2 of the objects, and then it is over r squared, or r is the distance between the centers of the objects. And to clarify, the system is the star and the surrounding is everything around the star, such as the black hole. And so part 1 of my code, I changed the seed as instructed to my GT email, kkm83@caltech.edu. My gravitational constant is 6.7 times 10 to the negative 11, which is always going to be the same. The mass of the star is changed to 2.0 times 10 to the 30. Delta T is 86,400 relative to Earth. T is equal to 0, and down here we calculate the velocity which was given to us, so nothing else to do here. And then more code for part 1. Here we calculated the velocity components, initial and final velocities, computed initial and final momentum vectors, calculated the star's change of velocity and change in momentum, which is delta V, delta P. And then we did delta P over delta T. And then down here, we used Newton's second law to calculate the net force. And then down here, we calculated delta P over delta T parallel. And then down here, we used Newton's second law to calculate the net force parallel. Calculated delta P over delta T perpendicular, using that Newton's second law to calculate F net, or net force perpendicular. And down here, we just found the mass of the black hole. And so from our simulation, as shown on the left, our estimated black hole, which was the average values, was 1.31 times 10 to the 34 kilograms. And down here, our net force was 9.18 times 10 to the 28, which is a combination of the net force perpendicular plus the F net force parallel. And so for part 2, we were given the masses and constants. We didn't have to change any of that. And we were also given initial conditions and everything. No need to change those. But then down here, we found the ship speed and ship for X and Y, or the ship's velocity, which we found using trial and error. And on our right here, it's more code for part 2, which we found position planet to moon, position a ship to moon, force planet on moon, force ship on moon, net force on moon, which is force of the ship on moon plus force of the planet on moon. And then going on to the next one, which is position planet to ship, position moon to ship, force planet on ship, force moon on ship, and then the net force of those two combined, like the last one. And then down here, we just found the moon's velocity, moon's position, ship velocity, ship position. And if everything is correct, we should not get that, oh no, you crashed into the moon. And as you can see on the left here, it is orbiting around the moon and the black hole. And there are some possible mistakes or errors that might change our data in this lab a little bit, is that there are no outside forces acting on the system during the simulation, meaning not all the forces are accounted for, which means it is not the most accurate. And for number 2, we guess and check the initial conditions of the spaceship, meaning there might be more accurate representations and numbers that fit better. And to discuss finally, we want to discuss how the net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. Well, they're completely the same. It's just that to calculate both of those values, We just need different numbers and values to calculate them. So for the net force and its components, we need all of the outside factors that influence the system. However, with the rate of change of momentum, to find its perpendicular and parallel components, we only need the system's velocity over motion. And if you wanted to predict the motion of the entire system, what would you need to include in your computational model? Well, in our computational model, we will need every force that in its surrounding that affects a system, no matter how small it is. Again, this is my lab submission. Thank you.